Myself, Mrs. S. Nusrath Najeeba, Assistant Professor, Department of Computer Science SF, the Standard Fireworks Rajaratnam College for Women, Savahasi. In this video lesson, we are going to learn about what is a deadlock and how it impacts in DBMS. Let's get into the video. These are the contents that we are going to cover in the video. First, we are going to see the introduction for the DBMS. And next the deadlock types in DBMS and the Kaufman conditions for a deadlock and how we are going to handle a deadlock. After that, we are going to see the best practices for avoiding deadlock and as always conclusion. Let's go with the introduction. In DBMS, continuous and efficient processing of transactions is crucial to data consistency and system performance. Deadlocks will likely be a major problem in multi-user database system. A deadlock occurs in a multi-user database environment when two or more transactions block each other indefinitely by each holding a resource that the other needs. This results in a cycle of dependency, that is a circular wait, where no transaction can proceed. Let's see it with an example. Consider the following image as an example for a database transaction. In this, we are having two transactions. First one is student, second one is grade. Okay. In this figure, we can see that T1, transaction 1 logs the resource student and needs the resource grade. That is, T1 having student resource and it needs the grade resource. So it holds the student database and gives a request to access the grade database. In the transaction 2, it holds the grade database and it needs the student database to process the transaction. So it sends a request to transaction 2. Here T1, that is transaction 1, waits for transaction 2 to complete to release the grade database, and the transaction 2 waits for transaction 1, that is T1, to release the student database. This results in a deadlock. Next, we are going to see the types of deadlock. There are two types of deadlocks in database management systems, such as resource deadlock and communication deadlock. First, let us see what is a resource deadlock. Resource deadlocks are experienced when process need access to the resource which happen to be held by other resource, leading to a deadlock. Let's take this example. Okay, in this, process A holding resource 1 and waiting for resource 2, and process B holding resource 2 and waiting for resource 1. Here we can see a cycle. In this, resource 1 that is assigned to process 1. Now process 1 needs resource 2. So it is waiting for resource 2. But the resource 2 is being assigned to process 2. So process 2 now needs resource 1. It creates a cycle. This is called a circular wait. So this is the main reason for deadlock. Next, communication deadlock. Communication deadlock are less common but can occur in distributed systems where process communicate through messages. Let's see it with an example. In this example, process A waits for a signal from B. B waits for a signal from C, and C waits for a signal from A. As each process depends on another to proceed, none can move forward. This creates a deadlock where all processes are stuck and unable to progress. The best example for a communication deadlock is our regular calls. In a regular call, when we are trying to call a person, that person is speaking to another person called as B. Okay, the person A is now talking to person B, and the person C is calling person A. So the person C will be on the wait and the call wait. So this creates a communication deadlock. Next, the Kaufman conditions for deadlock. Deadlock have 4 necessary conditions, and they are called Kaufman conditions. These conditions form the basis of explanation of deadlocks in DBMS, like mutual exclusion. The first condition is mutual exclusion. This says that any one resource should be utilized by a single process only. That is, any one resource should be utilized by a single process only. If there are many processes waiting for the same resource, then one process should lock the resource so that no other process can use it simultaneously. The next condition is hold and wait. This condition occurs when a process is using one resource and waiting for additional resource which is held by other processes. This creates a cycle where each process is waiting for resources that are locked by others. The third condition is no preemption. The no preemption is the condition where resources cannot be taken from a process by force. A process can only release a resource voluntarily after it has completed its task. Final condition is circular wait. This we have seen before. It is a condition where a set of processes are waiting for each other in a circular chain. That is, a process A waits for resource 1, process B waits for resource 2, and process C waits for resource 3, but ultimately they all depend on each other, causing a circular wait. Next, we are going to see how we are going to handle the deadlock in DBMS. In DBMS, it means management and understanding of deadlocks in such a way that they will not affect the performance and dependability of the system. There are several techniques to manage deadlocks effectively, like deadlock detection. First, let us see what is a deadlock detection. It is the activity of finding out if there are any process in a system waiting for one another and cannot proceed. A wait for graph. We call it as wait for graph. This graph can be used for this, and the system keeps track of which process are waiting for other process or resources. When it detects a cycle in the graph, it takes necessary measures against deadlock. Next, first we detect the deadlock. Next, deadlock prevention. Deadlock prevention is a method to ensure that processes do not get stuck waiting for each other and cannot move forward. It involves establishing rules to manage resource usage so that processes do not get into a deadlock situation. First, we detected the deadlock. Now we got to know how we are going to prevent the deadlock. Next, if a process got into deadlock, what we are going to do is the recovery. Let's see what is a deadlock recovery. This is the process of breaking a deadlock, which is when 2 or more transactions cannot proceed because they are waiting for resources held by other transactions. Now we are going to see how we are going to avoid the deadlock. Deadlock avoidance. This refers to proactive strategies and algorithms that ensure a DBMS never enters a deadlock state. Unlike detection or recovery, avoidance techniques analyze each resource request in advance and only grant it if doing so keeps the system in a safer state, where all the transactions can eventually complete without causing a deadlock. Okay, let us see what are the key concepts in a deadlock avoidance. First is safe and unsafe states. A system is in a safe state if there exists a sequence of transaction execution that allows every transaction to finish without causing a deadlock. An unsafe state does not guarantee this, though it may not be deadlocked yet. Second one is resource allocation graph, RAG. This is a directed graph representing transactions and resources. By analyzing the graph for cycles, the system can avoid granting requests that would lead to unsafe or deadlocked states. Third one is Banker's algorithm. The Banker's algorithm is a classic deadlock avoidance method. Before granting a resource, the DBMS simulates the allocation to check if the system remains in a safe state. If not, the request is denied or delayed. This approach requires advanced knowledge of each transaction's maximum resource needs. Next one is resource ordering. By enforcing a global order in which resources must be requested, circular wait, a Kaufman condition, which is prevented, reducing the risk of deadlocks. As well as the locking techniques. Using fine-grained locks such as a row level instead of table level and consistent lock acquisition order helps avoid deadlocks. Next, we are going to see the best practices for avoiding deadlocks. First one is using timeouts. When acquiring resources, use timeouts to avoid waiting indefinitely. If a source is not available within a certain time frame, the thread should release all acquired resources and try again later. The second practice is lock ordering. Establishes a consistent order for acquiring locks. For example, if two transactions need to access tables A and B, make sure they both lock A before B or vice versa. Last one is avoiding nested transactions. Minimize transactions that require access to multiple resources simultaneously. In conclusion, deadlocks in DBMS have significant performance and reliability effects. It is important to know the causes, conditions and control methods of deadlock such as deadlock detection, prevention and deadlock recovery to assure efficient database systems. Database administrators must adhere to good practices and stay up to date with the impact of deadlocks so that they can function well and lower risk in terms of deadlock occurrences. I hope you learned what is a deadlock and how deadlock impacts in DBMS through this video. Thank you for watching. Happy learning.